All right, so what is C minus C? 0, okay? That's a really bad 0. That's it. If we have the derivative of a constant, it's 0. And if you think about it, it should make sense because a derivative is a rate of change. And if we have a constant function, the change in y over the change in x is 0. It doesn't, it's horizontal. So we'll talk a little bit about different types of notation. So this is what happens when someone like discovers calculus and doesn't tell anyone, and then someone else thinks they discovered calculus and they did some things wrong. So Leibniz thought he discovered calculus and had some things that weren't quite right, and so Newton had to step forward and say, no, 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 you're wrong. And so there are different notations that are used. This notation d/dx just means the derivative with respect to x of whatever's in parentheses. So the derivative of a constant is 0. Almost exactly what I put up on top. Okay, well, I'm going to do that one next. Not next. I'm going to do this one first. How about find the derivative, the let's see if that helps. Find the derivative of f of x equals x. let's see, f of x minus f of a over x minus a. What do we get there? 1. So derivative of a constant is 0, derivative of x is 1. Derivative of x squared will be next. I'm going to give you a hint, it's not 2. I hate to, break your bubble on that one, but excuse me. All right, so for x squared. So limit as x approaches a for x squared. Take f of x minus f of a all over x minus a. Now, x squared minus a squared we can factor. And so we get whatever value we're approaching a plus a it would be 2a. In general, at a value x, then it would be 2 times x. All right, so other derivatives of power functions. So we've got the derivative of a function is 0, the derivative of x is 1, the derivative of x squared is 2x, the derivative of x cubed, anyone want to take a guess?
3x squared.
Why would you say that? 3x squared. x to the fourth, 4x cubed, x to the fifth, 5x to the fourth, x to the sixth. So what's the pattern?
Power in front of x, and then the new power is -1 and old one.
Excellent, excellent. Yeah, so one way that I've heard it described and that I like to use is you bring the power down and then you take x to 1 less power. And that will work every time you have a function that is x to some real number power. So it works for fractions. It works, or fractional exponents, I should say. It works for any real number power. So here it is in general. The derivative with respect to x of x to the power of n, as long as n is a real number, is n times x to the power of n minus 1. All right. So a couple other rules then that we can pull. If we have a constant times a function, the derivative of that is just going to be the constant times the derivative of the function. For instance, if we had 4x to the 7th, basically what you're going to do is ignore the 4 and take the derivative of x to the 7th power, and then at the end multiply that 4 back in. 28x to the 6th. Only works with constants. If we have a function times a function, that rule will come later. I know you can hardly wait. If we have function f and function g, and they are both differentiable, then the derivative of the sum is the derivative of the first function plus the derivative of the second function. Would 7x be 7 or would it still be 1? So 7x, so the derivative of x would be 1, and then you'd multiply by the 7. Yep, so it would be 7. All right, no, this is probably going to shock you, but the rule for if you have the difference of two functions is the derivative of the first function minus the derivative of the second. All right, so here you go. Take the derivative of x to the 8th plus 12x to the 5th minus 4x to the 4th plus 10x cubed minus 6x plus 5. So if I wanted to be very specific about this, this would be the derivative of x to the 8th plus 12 times the derivative of x to the 5th minus 4 times the derivative of x to the 4th plus 10 times the derivative of x cubed minus 6 times the derivative of x plus the derivative of 5. Now, how often do I expect you're going to write it out this way? None. Right, but this is technically what we do with this problem. what is the derivative of x to the 8th? There you go. And what if I take 12 times the derivative of x to the 5th? There we go. Then plus minus plus, yeah, we don't even write that then. There's the derivative. Now we could, if you were really feeling up for it, we could actually take the limit as h approaches 0 of f of x plus h minus f of x all divided by h and work that all out, because x plus h to the 8th power, that's not tough. Okay, it's a little bit tough. But this is just a nice, easy way to calculate that. Works better than the, it's just, it works the same as doing it with the definition, but it's a little bit quicker. Exponential functions. I'm pretty sure you've done some work with e and with logarithms and things. E has its own very special derivative.
Sorry.
All right, so the derivative of e to the x is e to the x. It's its own derivative, which is pretty unique. So if we have a function e to the x minus x, we're going to find the first derivative and the second derivative. By the way, for the AP exam, it is expected that you will have memorized what e to the 0 power is. Anyone know e to the 0? It's 1, right? Any number other than 0 to the 0 power is 1. It is expected that you know that the ln, the natural log of 1, is 0. And the natural log of e to any power is just that power. So if it's just e, the natural log of e is 1. All right, derivative of e to the x. E to the x, yeah. It didn't change from the last slide to this slide. It's still e to the x. Derivative of x. 1. There's our derivative. Second derivative. So for the second derivative, we just go back to the first derivative and take the derivative of that thing. So we have the derivative of e to the x. Yep. And then the derivative of minus 1, 0. What would the third derivative be? E to the x. And the fourth derivative? And the 572nd derivative? Yeah. So that e to the x is just going to keep coming back. All right. So here we have a little bit different problem. If f of x is equal to x squared plus 4x plus 3, all divided by the square root of x, find the derivative. No, we didn't have a rule that would help us with division. So what I would like to do is rewrite this so that it doesn't have division. And because my denominator is only one term, I can write this as x squared over x to the 1/2 plus 4x over x to the 1/2 plus 3 over x to the 1/2. And then simplify, if I can, each fraction. How do I simplify those powers? Give you a hint. It starts with sub and ends with tract. So I can subtract my exponents. 2 minus 1/2. Right, 3/2. Or 1 1/2. 1 minus 1/2. And this last term doesn't have an x in the numerator. So I could bring that x from the denominator up just by changing its sign. That's our function. Now I can take the derivative. Oh my goodness. Okay, so if you have a quotient at this point, we need to somehow write it as a sum or difference of some powers of x. Just like if we had a product, we would use FOIL, multiply it out, and then we can use our power rule to find the resulting derivative. There is a rule for quotients. There is a rule for products. That'll be Monday's assignment. Okay, but for right now, just using E and the power rule.